Hello everyone and welcome to this project video on the self-balancing robot. This video explains the robot's main components, the PID algorithm, and the electronic setup that allows it to maintain balance automatically.
The Arduino Uno microcontroller serves as the robo-brain. It receives the sensor data and calculates the corrective actions to be applied. This microcontroller is programmed to read the inclination measurement, determine the error relative to the vertical position, and adjust the motor speed to stabilize the robot. The MPU-5060 sensor is an EMU inertial measurement unit model that combines an accelerometer and gyroscope. The accelerometer measures the robot's inclination, while the gyroscope measures the rate of the rotation. These two combined pieces of information allow for precise knowledge of the robot position in space. The L298 motor driver model acts as the interface between the Arduino and the motor. Control the speed and direction of rotation for the two DC motors attached to the wheel. These motors ensure the robot's movement and corrects its balance by moving forward and backward as needed. The robot is powered by two 3.7-volt lithium batteries connected in serials to provide approximately 7.4 volts, which is sufficient to power the Arduino board and the motors. These batteries offer adequate runtime while remaining lightweight. The two yellow drive wheels are fixed directly into DC motors. Their rotation allows the robot to move and balance itself. If the robot leans forward, the motor turns forward to upright it, and vice versa when it leans backward. Chassis and connectors. All these elements are mounted on a 3D chassis, which serves as a mechanical support. The chassis holds components stable and centrally to ensure good balance. Connecting cables link the different models, and a switch allows the robot to turn on or off easily.
Now the project program. The program is divided into 5 key parts. First, we add libraries for the sensor and PID. Next, we define the variables to store the robot's angle. During startup, we initialize the sensor at 400 kHz. Finally, the main loop acts as the heart of the system. It constantly checks the angle and moves the motors to keep the robot upright. Now for the simulation. Before building the physical robot, we validate the design using Tinkercad circuits. The sensor connects via the I2C bus for high-speed data transfer. The Arduino sends signals to the driver to control the speed and direction of the motors.
First, we connect the DC motor with the L298N motor driver to regulate the movement between them. Next, we will connect the cable from the positive and negative battery port to the 12V and GND port of the L298-9 motor driver to allow power to flow into it. Then we take the 12V port of the motor driver and connect it to the VIN port of the Arduino, and we do the same thing with the GND of the Arduino and the GND of the motor driver. After that, we will connect the rest pins of the motor driver to the rest pieces of the Arduino in the following order. EN4 with the digital output number 4, EN3 with the digital output number 5 of the Arduino, EN2 with the digital output number 6, EN1 with the digital output number 7, ENB with the digital output number 10, ENA with the digital output number 11. Then we will connect the port of our MPE1615 sensor with the port of the Arduino in the following order. First of all, the VCC of the MPE1615 with 3.3 volt of the Arduino, and the GND with the GND, the SDA with A4, the SCL with A5, and the ENT with the digital output number 2 of the Arduino. And finally, we'll add the switch between the battery and the 12 volt power of the motor driver to control whether our robot start or stop. And finally, as you have seen the final result, the robot is well balanced. It remains stable on two wheels even when tilted on one direction. The DC motor rotates in the opposite direction.